and then on to a tenure-track job at McGill. Since 2008, she's been at Simon Fraser as a Canada Research Chair. She's going to tell us about the 2D stochastic Allen-Kahn equation.
Thank you very much, Toby. It's a real pleasure to be out here, and thank you for the opportunity to come back. So what I thought I'd do on this Friday afternoon is give you a talk that's not super technical, and I'm going to try and end this with a very non-technical section. So feel free to interrupt me at any point. And if you want technical details, please hold your fire till the very end. Probably. Okay, so this is joint work with Mark Fraser, who's currently at Duke University as a postdoc, and with Paul Tupper. So Mark did this work as part of his PhD thesis with me, and I'm very grateful for funding to the Canada Research Chairs Program, NSERC, and other funding agencies. But what this talk is really about is the relationship, shall we say, between applications, analysis, models, and numerics. And as applied mathematicians, this is what we hope. We hope that this graph is connected. We hope that everything talks to everything else, everything informs everything else. But the truth, especially out in the real world, is that's not always how it goes. Right? So scientists or engineers might tell you that what you're doing is pointless if you're doing analysis. The modelers might think the analysis is boring. The analysts might think the models are boring, et cetera, et cetera. You get the idea. Right? So the weights on these graphs might be suboptimal, shall we say. Okay, so that's what this talk is about. The discrepancy between how we think life should be and how it really is, and what might happen if you're naive enough to try and fix a controversy. So this is my talk. I'm going to tell you a little bit about a problem. I'm going to tell you about how we walked into a controversy without knowing that we were walking into a controversy. We tried to solve a hard problem. We found a simpler problem instead. I'll tell you what we tried with the whole problem, and then I'll end, as promised, with the non-technical section. Okay, so back to this picture that I had. For all of you who are taking a PDE class, you've probably seen a variant of this slide. So if you have a linear PDE model that comes from an application, if you study well-posedness, then you can say a great deal about its stability properties, about how it interacts with the data. And the source of all wisdom, Wikipedia, says that if a problem is well posed, then it stands a good chance of solution on a computer using a stable algorithm. If it is not well posed, it needs to be reformulated. Okay, so if Wikipedia says this, it must be true. All right, so if you haven't taken a PDE course, here's a quick refresher. We call a problem well posed if it has a solution. That's a good start. This is in itself quite a big question because we have to characterize what we mean by a solution. We'd like solutions to be unique, so we don't want too many of them floating around. And finally, we want that small changes in data only lead to small changes in output. Okay. And so here's an example. If you're trying to solve the Poisson problem in a domain with zero Dirichlet data, then what you do is you integrate the PDE against a function v, integrate by parts, remember all the calculus you had, and then you end up with something called a weak formulation right here. And the weak formulation often tells you what space or what kind of solution you should be looking for. So the choice of H over here will dictate whether you will find solutions or whether you won't. Okay, so maybe you've seen this before, maybe not, but I thought I'd refresh your mind. Consider a square, and you've got periodic boundary conditions. So anything starting from the bottom will reappear at the top. Anything starting from the left reappears on the right. We can call this a fancy thing. We call it a torus. Okay, so on the torus, you can expand functions in Fourier series in both directions. You can add up the Fourier coefficients, and that gives you a Fourier series right there. And so if you wanted to characterize a Sobolev space, a set in which you would look for solutions of the PDE, this is generic class in which you would look. You would look for solutions in the class HS, where the parameter S tells you how many of these pre-multipliers you hit your Fourier coefficients with. Okay? So whenever the series converges, you say that your function, whose Fourier series that is an HS. And so if S is positive, you have smooth functions, functions whose derivatives make sense. If S is negative, these are distribution value functions. And this is actually a very nice characterization because you can actually compute one of these things. So what you would do is you would compute the Fourier coefficients, and then you would square them and then multiply them by the right prefactor and add them up. That's what you do. And another way to say this is, say you're working with S equals 0. Instead of writing that, I'm just going to reformulate it in terms of something I'm going to call a radial energy density, ER. So ER is nothing but these coefficients times the scaling. Or if you were trying to implement this in a computer code, you add up all the energies corresponding to all the yellow points, and these yellow points are nothing but integer lattice points. Okay? So you add all those up, and that together gives you your norm. So if I know everything I need to know about this guy, I know everything I need to know about the Sobolev norm. So this talk is going to be focused around trying to compute energy radial densities. That's what I'm going to compute. Okay? So the Allen-Kahn equation is a really old equation. It's a wonderful model that gives you patterns. It describes the evolution of interfaces. And if you have no noise and no diffusion, then that's the equation. The change in the field hue is given by beta, some parameter, times u minus u cubed. So it's a nonlinear PDE. And here is a picture of what it might look like. Here's a movie. So the minute you add a Laplacian, this equation is going to try and push u to a system where it has interfaces between 0 and 1, but those interfaces are smoothed out. Okay, so it's going to have diffuse interfaces, but mostly it'll try to be either 0 or 1 with sort of a smooth variation between the two. Okay, so that was the classical Allen-Kahn. Now what we're going to try and do is look at a stochastic variant of this problem. And so if you haven't seen an SPDE before, the best way to think about it is to pretend that you're in a rock band in the Sahara Desert in a sandstorm. Right? So you're playing some music, and then you're strumming your guitar, and at every instant in time, your guitar is being hit by sand. So the effect of the sand on your string is that of the noise. Okay. So in particular, the models that people are really interested in are parabolic stochastic partial differential equations. Okay? So things that have something that looks like a Laplacian, some other term, and then the noise. I talked about the Allen-Kahn, so I'm going to look at the stochastic Allen-Kahn. So this is the same model as before, except now I have a little space-time white noise in there. So I'm going to be doing pattern formation, but I'm going to look at what happens if I kick in some noise at every point in space and time. So in 1D, this is a very well-studied problem. Okay? It's been theoretically analyzed. There's been a numerical analysis of it. You can show existence and uniqueness for it. And if you do computations, you can see that things are jiggly, but they are sort of doing the right thing. They're pattern forming. Okay. In 2D and higher, applied scientists or some applied scientists love it because it is one of a large class of problems called the Model A problems. It's used to model all sorts of critical phenomena. People love to do numerics on this model. So they'll do finite differencing, they'll do finite elements, they'll do spectral methods. All kinds of stuff is out there. Okay? Because what could be cooler? You've got a PDE, which gives you patterns, and then you throw some noise on it, so you've got some noisy patterns. Right? Sounds sensible. Mathematicians hate it. So mathematicians say that problems of this class in higher dimensions are supposed to be ill-posed. So people expect that these models will be ill-posed. They will not be well-posed. But they have asserted this for many classes of these models without proof. They have good reason to believe this, but the only proof that has been shown that I'm aware of is by Prado for the Kahn-Hilliard. This has not been done for the generic case. And so this is where we sort of naively wandered in. We thought we were going to do some numerics and some numerical analysis, and then sort of walked into a wall because the mathematician said, "Are you crazy? Why are you trying to do this? It's not even well posed." Okay, so here's the cartoon again. The application guys love it. The analysts hate it. The people that do numerics can't do numerics on the full model because you're working with space-time white noise. So what they do is they discretize, and then at every grid point, they add a little bit of noise. And as you refine your mesh, you add more and more noise. But what you're really doing when you do that is something called regularization. So people are studying a regularized version of this. So we thought, we're numerical analysts. We understand a little bit about numerical investigation. We understand a little bit about the model. Let's study the regularization. And then from this investigation, try and at least make this edge in the graph appear. Okay? So this is the Kahn-Hilliard equation. And what I've shown on the left is a discretization with 128 grid points, and on the right with 512. And this is also a pattern-forming PDE. I've got noise in it, and it looks kind of reasonable, right? So it is tending to form things that are either 0 or 1 with some sort of diffuse interfaces. But if you did the same sort of thing with the Allen-Kahn equation, say you had a grid with 32 or 128 points, and you started it off with the same initial condition. Okay? It's hard to see, or it's hard for me to say that this is a more refined version of this. Okay? It's hard for me to say that this is a converged solution. And if you're not convinced, look at this guy. This is the same problem with 256 points. Okay, so this is, it's doing a lot of horrible, interesting things. None of them look like pattern formation. Okay, so we wanted to understand. You have a generic parabolic SPDE with a nonlinearity to which you add white noise. Are these well posed in higher dimensions? And if they are, in what spaces do solutions live? And then finally, are these solutions physically meaningful? In other words, is the model even a good model? So we wanted to resolve the discrepancy between what practitioners do and what mathematicians think. Okay. So the next few slides are the slides where, in every talk you need to zone out a bit. So these are the talks, these are the slides in which you can zone out if you want. We started doing what we would have done for the Laplacian. We took the problem, we multiplied by a test function, and then we integrated by parts. More formally, we looked at what happened if we viewed this as an operator equation. It's not at all clear how to make sense of weak solutions for the stochastic Allen-Kahn, right? Because the measure in here is not a good measure. So what we do is regularize and work with the approximations. Here's something that should blow your mind. Okay? There is 0, and then there is 0. So something is called a zero distribution if when you act it on any C infinity function, you get 0. Okay, so you take a function, you integrate against function phi, you should get 0. So u equals 0 as a solution. But so is something that's infinitely rough. So if you take the limit as n goes to infinity of sine nx, that thing oscillates infinitely fast. You multiply any test function and integrate, you're going to converge to 0. So, in other words, this guy is 0 in the sense of distributions. And we wondered whether this is 0 in the sense of distributions. This is the solution to the Allen-Kahn equations that we compute. And our question was, well, this looks kind of like 0, just in the sense of distributions. So that's the main conjecture. The approximations of the stochastic Allen-Kahn converge to a 0 distribution. Okay, so I have to tell you how we actually went about trying to analyze this, because I was trained as a numerical analyst. So you first have to look at every bit of your equation carefully. And what we realized pretty quick was that white noise is really noisy. Okay? Maybe everybody here knew that, but white noise is the derivative somehow of a Wiener process. If you don't know what a Wiener process is, don't worry about it. This is all you need to focus on. This W term is the sum of a Fourier series, and the Fourier coefficients beta are all of the same size. Okay? So these are IID Brownian motions. For any decent self-respecting Fourier series, the Fourier coefficients should decrease as k increases. Right? The higher modes should become smaller and smaller. Here they don't. Here they're all the same magnitude. So this is a really, really, really bad thing. So, okay, so this is bad. So what do? Well, you do what you would do if you encounter a Fourier series, you chop it off. You cut off the tail. Okay? So we regularize the noise. Okay? So now we have a slightly different PDE than the original one we started out with. We've got the Allen-Kahn, and then we've got this sort of regularized noise, and then we're going to let n go to infinity. Okay. So we're going to look at it in Fourier space, and we expect that our numerical methods will give us solutions which in the limit converge to the same place that the actual solution is converged to. Well, the original problem was too hard. So what we did was we said, okay, let's go back. Let's take the stochastic Allen-Kahn equation and look at simpler variants of it. Okay? So I've dropped the nonlinear term here, and what I have is the heat equation with noise. This is the linear variant of the Allen-Kahn with noise. The analysis for this has been done by Walsh, and it's sort of well studied. And we thought, okay, let's try and do numerics on this. So just a reminder, the S norm, the S norm of function u is determined by its energy radial density, and that's what we're going to compute. So the energy radial density is right there. If this integral here converges, then this norm is finite. Now, we did numerics, and so here's the line of the numerics as a function of r. You compute the energy radial density, it's just simple addition. Here's the line 1 over r squared. This is a log-log plot. And you can see that the energy radial density seems to be going like 1 over r squared. Which means that if you stare at this integral, this is like 1 plus r squared to the power s. This is like 1 over r squared times r. For this integral to converge, s has to be less than 0, which means that solutions of this problem are not even square integrable. Okay. So, the solution for the stochastic heat equation is in the class HS for all s which are less than 0, almost surely in probability. So that's bad news, because we think of the heat equation as a smoothing, wonderful thing, but here it's not. Okay? The solutions are distribution valued. So now you throw away the Laplacian term and you look at the fully nonlinear problem. And this one is a slightly bigger mess. You can analyze it. I implore you, don't read through the details. The conclusion is important. The conclusion is that in the steady state, these regularized solutions converge to something. And as long as S is strictly less than minus 1/4, the limit is in HS. Moreover, the thing that it's converging to is a zero distribution. Okay? So the regularized solutions of the decoupled Alencon converge to zero in a very weak norm. So, you deserve a break. So here's the Kahn-Hilliard with noise on a sphere, and on the other side on some weird jiggly object. Okay, so now we're going to look at the whole problem. Okay. So this is the full stochastic Alencon. Everything's in there. We're going to chop off the noise as before. And then, just to remind you, when you had only the Laplacian, you converge to a non-trivial distribution. When you have only the nonlinearity, you converge to a zero distribution. And the big question is, what happens if you put everything together? And so we had some heuristic reason to believe that the energy density looked like that. So for the regularized solution, the energy density looked like that. That's what we believed. How and why we believe this is a different talk. So we have this guess. So what are we going to do? We're going to fix R, and we're going to look at what happens as N becomes big. Then we're going to fix N, and then look at what happens as R changes. Right? It's the obvious thing to do. So this is what happens if you fix capital N and change the R. So for fixed N and R changing, that's what you get. So these things are decreasing. As N increases, these things decrease, but very, very, very slowly. And so the decay is in agreement with this sort of behavior. And we actually verified this doing fitting on these graphs. If you fix N and let R change, then this is what it looks like. And so altogether, what we have is that the energy radial density, we conjecture, actually looks like this. It looks like 1 over log n plus r squared. This decays very, very slowly. And so if you're trying to sum this series with s equals 0, you're going to go to infinity. Okay? And if you're trying to sum this for any s which is smaller than 0, then by the dominated convergence theorem, you're going to go to 0. So that was the reason why we came to this big conjecture. The big conjecture is that the stochastic Alencon equation is not a good idea in 2D. Okay? So for all times and all s is smaller than 0, the regularized solutions are in HS, and they converge to 0 in probability. And as a corollary, yeah, it's not interesting. So that's the short technical summary. Using numerics, we were able to try and say something about a long outstanding controversy. The conjecture about the fact that the solutions of the stochastic Alencon equation are not interesting was subsequently proved by Mark with some collaborators, including Martin Heyer. And the implications are that as a model, this is not a pattern-forming model. It doesn't matter what initial condition you start from, you're always just going to 0. It's not useful. It's uninteresting, I guess, but this is where we are not getting a lot of love. Right? All right, so maybe I should take some questions before I show pictures.
So let's thank the speaker.
George.
you have this convergence for S less than -1/4, right?
For the decoupled Alencon.
Decouple. How about the S equal to -1/4? What can you say?
It blows up. Yeah.
So that blows
So
up
the result
also
is sharp.
bigger than equal to -1/4.
Yes.
So for the non-stochastic Cahn-Hilliard equation, I have some physical intuition about why you get pushed to a 1 or a 0.
Right.
Think about that double level potential.
Right.
Do you have any intuition about what's going on here in 2D when you have this noise?
Yes. So I think what's going on is that physically you should not be uncorrelated from your neighbors. So when you're pattern forming, particularly if you've got something like the Alencon, where you've got a term that's got you communicating with your neighbors, right? You've got this diffusion thing going on. The white noise says that the kick that you get at every space is completely uncorrelated with what's happening to your neighbors. So that you would be driven to a pattern forming system at all is not clear. So that was my intuition. And I think a more realistic model here is one with colored noise, where you say that you do have noise, but that it's correlated with the neighbors over some length scale.
So you have this nonlinear term, FU.
Yep.
Do you need some criteria on the derivative of FU?
So in many of these pattern forming models, the derivative is very nice as a functional derivative. So f of u is, in this case, u minus u cubed. So these are very nice polynomial type things.
So you don't need an f prime at the 0 equals 0.
You don't, it doesn't have to be. So you could set it up so that you are driven to two different steady states. So those would be the zeros of f prime.
One more question?
This is probably a somewhat basic question. Oh, is there a simple application you have in mind where this thing arises?
Well,
you probably have several, but
okay. So one interesting thing that happens is I am told that when embryos develop, you can see pattern formation happening on the surface of the embryos, right? And why are these patterns forming? It's some sort of chemical kinetic description. But pattern forming models are around in a lot of different places. But that's one interesting example to keep in mind.
So let's thank Nilima again.
Yep.
Something non-random ready for us, I believe.
Yep. So I learned, to my shock and horror, that we are the fighting blue chickens. Did you know that? Chickens. Okay. So these are some of the people I went to school with, and I thought that since I'm back, I should show you what it is we are doing now. So this is Ewing Hall. I think you can recognize that. Yeah. Many of the people in here have less hair than they used to, but they're all doing really well. There was romance in our times. This was a former graduate student. This was another former graduate student. They got married while in grad school. Gamze was right next door to me, and she is now in Turkey. That is a picture of Keith and Doug when they were grad students, and now he's department chair at University of Mary Washington. This is an eminent researcher and another eminent researcher in the times when they didn't know how to eat cake without getting it all over their faces. So Julie is actually she's doing incredible work in math education at the University of South Alabama. Owen was a couple of years ahead of us, and I think he was a student of Gary Ebert's and Felix's. Yeah. So that's 2 chairs right there. Joe was a chair in his department. We used to be in room 320 in Ewing Hall. These 2 guys used to chew tobacco in that office. This was a visiting undergrad. I forgot her name. Maybe you can recognize who that is.
You know who your undergrad was?
Hmm?
I think that was Packy Simonager.
Oh yeah.
She was from Thailand. She did undergraduate thesis.
Right. Funky. I could not for the life of me remember. I had a whale of a time here. So if you've been to school here, you're really lucky. And if you're thinking of coming here, you're also making a good choice. Because I got a fantastic education. So many of these people I never took a course with, but certainly she took me on a road trip. She heard me complain about a lot of things. He heard me complain about a lot of things. In fact, I think memorably after one of my disastrous qualifier attempts, he suggested that I not give up quite yet. So I'm thankful. I think Rich was just starting his career at the time, so he was in the office just about as late as we were. Do you recognize him?
I had more hair then.
I don't know if any of you recognize him. Dick Weiner?
You might have taken that picture last week, actually.
This one, thank you, Debbie. So that was Dave Hallenbeck. Everybody remember her? That's Pam. Yeah. Him.
I have no idea.
And I've been asked by Debbie to suggest that this person consider reverting to his old look.
That mustache looks like it's been put on by magic marker,
It has
actually.
not. So for those of you, if you know, don't say, but can you guess? Sherlock Holmes. Yeah, I took finite elements from Maxwell's equations with Sherlock Holmes, yeah. All right, and so this was my supervisor, and Bob was somebody I took a lot of PDE classes with. So I had a great time here. Thank you.
I can wing it. This is easy. There we go. Our next speaker is Nick Brubaker. As many of you know, Nick is going to be an NSF postdoctoral fellow at the University of Arizona this fall. Nick's going to speak about capillary origami.
Thank you. This is actually some of the work that, preliminary stuff that hopefully I'll be doing out there, and this is work with John Plesko, my advisor, and so this is some preliminary stages. I'll talk about modeling it. It's about capillary origami. If you can guess from his work, it's a lot of coupling soap bubbles with other things and seeing what happens. So hopefully at the end you'll see a picture of a soap bubble. So, so first, research-wise, this is motivated by small-scale fabrication. So in the literature, and the problem making 3D structures on a small scale. So a lot of the way to do that is, in a small scale, it's easy to fabricate planar surfaces, right? So you can fabricate those in different ways. And a lot of times you end up layering it, and then you'll etch something off, layer it again, etch it off, and then you'll do this long process and come up with some planar structure that you can use. Of course, for making 3D structures, this doesn't work very well because you're still more or less working at a planar level. So another proposed method then was, okay,